Hello everyone and welcome to another session of Abaqus tutorial. In this session we are going to simulate rotary bending process. As you can see in this picture, the assembly consists of 5 parts. The part in the top is the upper die. The second part is the rocker. The third part is the blank, which is the sheet we want to bend and deform it. The fourth part is the lower die, and the fifth part is the rocker holder, which is located in here. As you can see, after the upper die is pushed down due to the contact between the rocker and the blank, and because of this assembly, which this part under the blank is empty, the rocker begins to turn and it shapes the blank similar to the outer part of the lower die. So the model we are going to get is like this. This is the result of our simulation. As you can see, the upper die is pushed down, and due to displacement of the upper die, the rocker is going to turn, and because of the contact between the rocker and the sheet is deformed like the outer part and outer side of this lower die. The second thing we want to talk about is a springback. Springback is the geometric change made to a part at the end of the forming process when the part has been released from the forces of the forming tool. Simply put, springback occurs when the material angularly tries to return to its original shape after being bent. There are too many reasons to this. First is the displacement of molecules within the material. As the material bends, the inner region is compressed while the outer region is stretched. So the molecular density in one side is greater than the other side. The tensile force on the outside of the bend is larger than the compressive forces inside it, and this causes the material to try to return to its flat position. Second reason is plastic elastic characteristic of metal. Any deformation of sheet metal at room temperature will have both elastic and plastic deformation, and after the bending tools are removed, the elastic deformation will be released and only the plastic deformation will remain. The release of elastic deformation is the springback often observed at the end of a metal forming process. The tensile strengths and thickness of the material, type of tooling, and the type of bending greatly influence springback. Efficiently predicting and accounting for springback is critical. Simulation softwares can detect springback and can also compensate for it. In this way, tooling processes are improved and manufacturing costs are significantly decreased. So the simulation of a springback is going to be like this. As you can see, after the blank has reached to the shape of the lower die, and after the tools are removed, it tries to get back to its flat position, but of course it cannot. It can only release the elastic stresses, and so the deformation is going to be like this. So we can start with creating the parts. In this drawing, each of the parts are shown and the dimensions are in metric system. So if you want to model the parts, you can pause here and use this drawing for creating each of the parts. Okay. We start Abaqus and we start by creating the blank, which is a 3D deformable solid extrusion, and the approximate size is going to be this 0.2 since we are using metric system. And the depth is going to be 0.1, and the blank is a square with the thickness of 2 millimeters. The next part is the upper die. So, upper die, which is a 3D discrete rigid solid extrusion body, and the approximate size is 0.6. Okay. We want these two lines to be equal. And we have a circle, we have a semicircle in here. Now is the dimensions. This line is 0.50. This line is 0.02. Okay, and the depth is equal to 0.1. Do not forget changing to shell for rigid bodies and assigning reference points. Next part is the rocker holder, which again is a 3D discrete rigid solid extrusion body, and the approximate size is 0.1. This angle is 70 degrees. Okay. This is the rocker holder, which again we must make it shell from solid and assign a reference point to it. Next is the lower die, a 3D discrete rigid solid extrusion body with approximate size equal to 0.3. and we must add a fillet in here using this. The fillet radius is equal to 0.004, 4 millimeters, and it's located in here. This dimension is equal to this, which is it makes the sketch over defined, so I just delete this one. Okay. Done. The depth is equal to 10 centimeters. Again, creating shell from solid and assigning a reference point. So the next part is the rocker. I could consider the rocker as a 3D discrete rigid solid extrusion body, as we did for all the other parts of the die, because the deformation is not important for us in this part. But here I'm going to consider it as a deformable body, and I will explain the reason later, but first modeling this part. According to the drawings, the rocker consists of a circle, which I want to fix here, and the radius of the circle is 5 centimeters. Then I want to add a construction here. We are going to have a fillet in here, but first we have to trim this part and add this fillet. The fillet is added. You can do the same for this side. Sorry. First I should trim this part. Next. Okay. Depth equal to 10 centimeters. Okay. Now the rocker is created. The reason I considered the rocker as a deformable body is because, as you know, we are simulating rotary bending. So during the simulation, the rocker experiences an orientation. For Abaqus to understand and consider this orientation, it needs to know the mass and the moment of inertia of the rocker. When you model the rocker as a discrete rigid body, you have to assign it, change it to a shell, as we did for all the other discrete rigid bodies or rigid bodies. And when you assign a shell to it and you change it to a shell, then you don't assign any property to it, and so this part will not have any moment of inertia. You have okay, you can add the moment of inertia in the interaction module, but because this is not a very simple body, you have to calculate it handedly or with other softwares. The easier way, the other way, which is the easier way, is to consider the rocker as a deformable body, as a solid deformable body, and assign property and other things to it, so the Abaqus can calculate the mass and moment of inertia of this part itself. So you don't have to assign it to the part, and the Abaqus calculates it itself, and then it can easily consider the rotation of this part. So considering the rocker as a deformable 3D solid body, it makes it easier for us, and we can just adjust a stronger and stiffer material type to it. So then we have approximately considered it as a so next we go to property module and create materials for rocker and the blank itself. First material is named blank. Elasticity, (120 gigapascals) and 0.35 for Poisson's ratio. And plasticity, plastic, okay. Creating a section, a solid homogeneous section, name it as section blank. Assign it to blank. Next, create another material named as a steel. Density is equal to elastic property 213 gigapascals and 0.3 for Poisson's ratio. Section steel, solid homogeneous, and we assign it to the rocker. Because the rocker won't experience a high strain, we don't have to consider the plastic properties of this material. Next, before going to assembly module, we should create a partition on one surface of the blank. So we use partition face, and partition is a straight line 4 centimeters far from this side. Okay. Then go to assembly module. First, I want to translate the blank into the origin. This point here. And then I will adjust the placement of the lower die. Okay. Then the rocker, which is coincident inside this upper die, and the rocker holder. I want to tangent this face of the rocker holder to the rocker. So for this reason, I use the command translate to. The face of the movable instance is this face of the rocker holder, and the face of the fixed instance is this face of the rocker. The direction of the displacement or contact is this direction, and the clearance is 0. Done. Okay, now it's tangent. So next we should assign the placement of this assembly, but first let me translate this lower die and the blank from here to the origin. Sorry, from here. Okay, now the part, now this assembly is translated to here, and then I choose translate again, choosing these 3 parts, and first I move here, this point to this point. And then once again using translate and choosing these 3 parts, now I want to define the vector of this translation. The first vector is this point in here, which is now the origin, so 0, 0, 0. And the second point is minus 12 millimeters x direction and 500 minus 6 y direction. So, okay. What happened? Sorry. The first location is here, and the second is 12 millimeters. I have added 12 meters minus 3. Okay. Now, okay. Now it's correct. And we have a small gap in here. Okay. Next, we should go to step module and create the step. We define a dynamic explicit step with time period equal to minus 0.1. Okay, so next is the interaction module. Let's go to interaction module. First, we should create two interaction properties with two different coefficients of friction. Okay, interaction property O1 is contact. I want a tangential behavior, and friction formulation is penalty. Friction coefficient is equal to 0.1. Okay, the second interaction property is interaction prop O3, which is contact type, and again the tangential behavior penalty, and the friction coefficient is 0.3. Okay. Then we are going to create the interactions. Surface to surface contact. The first surface is the inner surface of this upper die. So let me choosing the upper die and clicking on replace. So only the upper die is left, this surface, and then invert display, and anything except the upper die is shown. The second surface is, sorry, okay, it's brown. The second surface is surface top, this face. Done. The mechanical constraint formulation is penalty contact method, and the interaction property is interpop O1. Okay. Again, the other contact is surface to surface. First surface is this surface of the rocker holder, brown, and the second surface is again this surface of the rocker. Again, penalty contact method and interpop O1. Another contact is again surface to surface contact, the contact between the blank and the rocker holder, the rocker. Okay, first we choose the surfaces of the rocker which will be in contact with the blank. These surfaces, done. And the second surface is this surface. Penalty contact method, and here interpop O3. And final contact is the contact between the lower face of the blank and the lower die. So again, surface to surface. These faces, done. Brown. The lower surface of the blank, done. Penalty contact method and interpop O3. Okay, there is another contact between the rocker holder and the upper die, but we are going to consider it as a tie because these two are always together, and in real life they are screwed together. So we are going to use create constraint and tie. Continue. The master is this surface of the upper die, okay, brown, and the slave is, again, let me remove the upper die, this surface of the rocker holder, brown. Okay, done. All the interaction and constraints are defined in interaction. So next is the load module, in which we should define the boundary condition and displacement. First boundary condition is defined for the blank, which is an encaster boundary condition in this area of the blank. Okay, the second boundary condition is a fixed boundary condition for the lower die. So again, create boundary condition. This point is encastered, the reference point of the lower die. The third boundary condition is the displacement of the assembly of the upper die, rocker, and the rocker holder. So again, create boundary condition, this time displacement rotation. We should choose this point of the upper die, and okay. Sorry. The step is the step in which the boundary condition must be created is the step 1. So here I should choose step 1, displacement rotation, this point again. And now, as you can see, I can define the displacement of each of the direction or rotations. U1 is 0, U3, UR1, UR2, and UR3 are 0 as well. And U2 is has a displacement equal to minus 0.03715. Okay. Because our step is an explicit step, we should define an amplitude. So here we click on create amplitude, tabular, and I want it to be a simple amplitude. So 0 amplitude, and at the time period, which is 0.1, the amplitude is 1. Okay. Choosing amp1 and okay. So the loads and boundary conditions are defined. So next is mesh module, and we should mesh the parts one by one in here. First is the blank. The approximate global size is equal to 2 millimeters. Assigning mesh controls, hex structure is okay, and assigning element type. Because the step is explicit, all the element libraries should be on explicit. Okay. As you can see, these settings will result in 1 element in the thickness of the blank. I want to increase this number to 3 elements. So using seed edges and selecting these edges. First, I should delete the meshes I've already added and wireframe. Okay, seed edges. 1, 2, 3, and 4. Method by number, and bias is on none. Number of elements, I want to be 3 elements. Apply, okay. And once again, mesh part. Yes. Next part is the lower die. Seed part. 5.5 millimeters is okay. Assigning mesh controls. Quad, free and medial axis, Okay. Assigning element type, explicit and linear is okay. So mesh part. Okay. Next, the rocker. The global size must be equal to 6 millimeters. Assigning mesh controls. I want hex element shape, sweep, and advancing front algorithm. Okay. And assigning element type, explicit. Okay. Mesh part. Next, the rocker holder. The global size is 1 centimeters, which is okay to me. And the mesh controls, quad, free, and medial axis. Okay. And assigning element type. Element library, explicit again. Done. Okay. Now all the parts are meshed, but the upper die. See part, approximate global size is equal to 7 millimeters. Assigning mesh control, quad, free and medial axis. Okay. Assigning element type, explicit. Okay. Mesh part, yes. After meshing all the parts, you can see the meshed parts and the assembly. The last module is the job module. In here, we should create a new job, job 1, model 1, continue. And using parallelization, I want 4 CPUs to work on this problem, and so the solver can solve the problem faster. Okay. And first do data check. To see if everything is okay. As you can see here, the check is completed and no warning or errors has occurred, so I can continue and submit the model. I have already another job named job 1, so I don't want this job to be the same name and to be overwritten, so I want to change the name of this job to job RB, means rotary bending. Okay, and continue. Oh, first, let me, because I have renamed the job, I cannot continue. I should submit the model. Okay, the model is submitted and running. I will show you the results after the job is done. Okay, so after the job is completed, we can see the results in the visualization module. In here, by clicking on plot counters on the form sheet, we can see the job, the result of this process. Let me animate the result. Play once, apply. Okay. Okay, as you can see, while the upper die is moving downward on the vertical direction due to the contact between the rocker and the upper die, and again the rocker and the upper face of the blank sheet, the rocker experiences a rotation, and this rotation shapes the blank as the similar to the outer side of the lower die. So here you can see the results as well. Okay, so followed by this session, there is another session in which we want to uh, explain and calculate the Springback phenomena, which occurs in this blank metal and in this sheet metal. So stay tuned and follow us in the next video.